Article number, well, I think 35. Yeah, article number 35. If you can type it in and make sure you're able to get this output, we'll begin our discussion there. Yeah. Article number 35. So you'll have to do some typing of the code on your own. It's not directly copy paste. So I'll give you maybe 15 minutes for everyone to work on it. 35. Same code you can execute. But only till here. Don't run the full thing. Only till the first 2, 3 blocks and getting this diagram. That's all for now. Because I want to set the motivation for a decision tree. So we'll not run through the entire code. We'll just run these two set of codes to get this tree. Article number 35. Are we done, everyone? We have the tree. Anyone needs more time? Everybody's done, right? Okay, so let's begin the interpretation of this, and that's what the tree is, right? So first of all, any insights from this? I mean, I don't want to talk about the code, but I just want to talk about this picture. Any insights anybody can bring up?
It's on the impurity of a particular node. Impurity means how classes are means that if there are many classes, then it is impure. If there is only one class, it is pure. And we measure this impurity and purity using entropy or Gini index. So there is a formula for entropy. So proportional of that particular minus.
Yeah, we'll discuss all of that, but high level insights.
So how impure the nodes are. If my entropy or Gini index are 0, means that node is a leaf node. That is pure node. Means only one class is there. If Gini index or entropy is 1, means this is highly impure data. We need to split further.
Yeah, so let's talk about the big picture without going in the impurity or the Gini. Yes or no? Okay, yeah. What else? Yeah, so this is the entire iris data set, right? So if you remember, we had 50 Setosa, 50 Varsicolor, and 50 Virginica, right? Everybody remembers that data? So over here, you're beginning with your original data, 50, 50, 50. Is that clear? What happens over here in this?
How many data, how many samples are satisfied on that particular 50 samples are satisfied.
Hmm.
And among the 50 samples, only 50 values are Setosa, like Gini index we are calculating. Gini is 50, sorry, 0. Means only one class belongs to that particular category. So this is one leaf node, and right side is if petal length is greater than 2.45 and petal width is less than 1.75. With this category, samples, 100 samples are satisfied this condition.
Okay.
Again, we calculate the Gini index and all this.
Yeah, we'll come to the Guinea in a minute. So like 50, 50, 50 flowers each. This is the first root node of the parent node. Root node meaning, I mean, the branch basically, like, I mean, you're breaking it down further, right? So this is the parent node, then this is the branch coming out from there. Over here, you can see it has the decision tree has done the separation where all the Setosa flowers are over here and versicolor and virginica flowers are over there. So it has done the classification for you, right? So what was the main objective? That I want to separate the 50 Setosa, Varsicolor, and Virginica in different classes, right? There are 3 classes. That's all basically we're doing. So you can see Setosa has been separated, Varsicolor, Virginica are in a different branch. Now this is not broken out further because there is no impurity or mixed flowers. Everything is Setosa, so it's not broken. But this is broken for forward because there is a 50 Varsicolor, 50 Virginica, and then so on and so forth. And you can see it keeps on doing that until it finds pure and pure node, right? How do you mean the pure? So if I have 50, 50, 50, all 3 classes are equal times. So that will be a higher impurity. If I have only 50 flowers of one kind, then it's a 100% pure system, right? So that's all basically it is trying to do. And the color coding, anyone can tell me about the colors? You see some different colors. Hmm? Yeah, so orange in this case is Setosa, and you can change that in the decision tree. And then green is what? Green is Versi, and then purple or blue is Virginica, right? Clear? Why is this white? Yeah, because it's like, when you mix these colors, orange, blue, green, and all of that, I mean, somewhere it's saying, it's all mixed up. So that's why it's white. As the branches become more clear, more uniform, the color becomes brighter, right? No, no, no. So it says Setosa, but you can see there is slight problem in terms of how they represent. So this is the like one class, but you can see 50, 50, 50, and total samples in this node is 150. You see that? So total samples in this node are 150, and then we have 50, 50, 50, right? No, no, no. That's right. That's right. So similarly, when you're going to do the exercise for Titanic, it will say 0 and 1, right? And then you'll keep on separating the zeros and ones and zeros and ones. So you'll see more and more like nodes and branches will be created from that point of view. But the main idea is that you begin with the parent node, then you have the branch nodes, and then you have the end node. This is called a leaf node in a decision tree, right? Because there's nothing else that can really come out from there. So it's a leaf. It's not a branch. It's a leaf, right? End node. Similarly, you have other nodes over here that you'll keep on going down. Is this clear? At least like visually what the decision tree is, right? Hmm. No, no, no. I mean, I'll explain that. So the way you're going to read that, I mean, we will talk about this when we go through the paper that I'm going to share with you, the document, right? I mean, I had that on my blog, but somehow it's like, taken away. And this is the total number of samples. total number of samples, right? This is how many each type we have. So for example, over here, it says you have 50 setosa, 50 versicolor, 50 virginica. Exactly. Yeah. Over here, 0 setosa, 50 versicolor, 50 virginica, right? And the way it is just saying this one is basically what is the dominant class, which is more number of times, or if it is not dominant, whatever comes alphabetically first. So setosa came alphabetically first, so that's why it was mentioning setosa, right? So majority class will be the one which is being defined. And then this is the criteria on which it is splitting. So I'll come to when we look into the algorithm. So it is saying that if I apply this criteria of petal length less than or equal to 2.5, 2.45, if you follow this criteria, what is the petal length? Anyone who remembers that flower? Yeah. So let's look at the flower one more time. Iris data set, right? We can see this. This is the petal, right? So what is the length? What is the width? And then sepal is the portion that comes down. So what is the length? What is the width? Clear? And then if you remember, we had all three flowers also somewhere where I can show you all three of them. Yeah, there it is, right? So which one is the baby flower here? The smallest one? Setosa, right? Which one is the heaviest one? Versicolor, right? And then Virginica is in between. So Setosa is the tiniest flower, even though they all are the same flower. Just because of the different variety or the species of the flower, Setosa tends to be smaller. Versicolor tends to be the highest or the biggest flower, and then Virginica is somewhere in between. Clear in terms of the flower. So now let's go back to this tree. This tree over here, right? Yeah, so it will be helpful if you understand some of those, but I'm just trying to explain you how decision tree really thinks, and then we'll go and do some of the math around that. Yeah, that's right. That's right. So it will help you make sense out of the data that is coming out. So if you do the ED, understand the data, understand the, like pictorially, you can relate to your data, then it's always easier. Sorry, Pawan. I will talk about that in a minute. But let's assume the condition, we know how it comes in, right? So what does the tree do? Basically, it says if you are a flower which is less than or equal to 2.45 petal length, all of those flowers will come on the left side. And if you're not following that criteria, then all of those flowers will come on the right side. So true, this criteria is met, you come on the left side. False, you come on the right side. So it says any flower which is less than or equal to 2.45, all of them you're coming over here. And the only flower which meets that criteria is Setosa. All the Varsicola and Virginica flowers have the length more than 2.45, right? So you can see immediately decision tree has come out with a rule which gives you a very good separation between the different classes. Ultimately, what is the objective of a classification model? To separate the classes from each other, right? So if I can tell the good from the bad, survival from the non-survivor, defaulter from the non-defaulter, all of that. So immediately it has applied that criteria and done the separation. And then it does this using this impurity measure, which I'll be explaining after we go through the document. So is everyone clear what is happening over here and what are these numbers? This is the criteria which was used to split the node forward. This is the overall number of samples in this node. This is the breakup. This is the majority class or the alphabetical class. Right? Over here, you can do the width also, but the tree is going to choose that for you. There are some trees where you can do your own custom as well, which I'll if time permits, I can show you. And then over here, what is the criteria it is splitting for? Petal width. It is splitting now on the petal width. So if it says if your petal width is less than or equal to 0.75, 1.75, you please come on this side, true. And if you're bigger than this, you come on the other side, which is false. So let's look at what exactly comes out from over here. So you can see the second criteria, which is helping us get a very good separation in the flowers, is the petal width. So it says if your petal width is less than this, all of you please come over here. So which are the flowers majority who are coming in? Versicolor. So we got 54 such flowers and 49 of them are versicolor, right? And if you remember this image, versicolor was the versicolor was this flower over here, right? So like, I mean, the petal is slightly different over here compared to the virginica. So even though the sepal length is bigger, somehow the petal width is smaller for this flower. So coming to this point, which is says if you are following this criteria, then you're gonna be versicolor more likely, otherwise you're gonna be virginica, and it continues to split forward and forward and forward. It will choose by itself. So that's where I'm going to share this document with Abhi, because I think there's a lot of question around that area, how we do this and what exactly it is. So I will share this and do, I mean, I had this in my blog, but I noticed that because I did not renew one domain, so it got taken away. So, just a second. I think it was 35. Yeah.
Less than 4.95. We are having value for among 54, we are having 49 versicolor and 5 virginica. So why it is showing class versicolor? Because it is mixed, right? So it should be.
No, it is showing the majority class. So what is the majority over here? So it's majority of the versicolor, right? So I was saying I had a very good article to explain all these metrics and everything that was over here, decision tree basics and modeling. I'll share that PPT down the road, but because I did not renew this domain, it got eaten away, right? So that's where. But anyways, not a problem. So what I've done is I have created a new document, which is equally good, which I'm gonna share with Abhi, and Abhi will be happy to share with you guys. So go ahead and take a read of this document, and then we will begin the actual exercise on Titanic data. Again, this is part of your in-class assignment. So remember the logistic regression you've done, you'll just add on the Titanic code in there, right? So take about 10 minutes and let's see who wants to explain. They will get +2 points. Whatever you understood. So this is the document that you'll be getting.
Sunny,
Windy, yeah.
So there, how we have calculated like information gain, then we need.
Same thing, same thing, same thing, yeah. Go through the document, then we'll discuss one by one. Shall we? Or we need more time? Shall we do a random number picker? Sachin has been selected. Go ahead. You want to try or you are still reading? Okay, yeah, whatever you want to share, yeah. No, no, you can just verbalize that. Whatever you have understood.
Classify. We have so we have multiple features. So we need to identify which feature we are using to best determine to classify the data. So based on that, we will recursively go ahead. We will classify the data. So we have two indexes in order to find out how pure the data is once it is divided. So one is Gini index and the other is entropy. So basically, Gini index, wherever if it is less, that means it is if it is closer to zero, that is more pure. And same with entropy as well. It measures the level of disorder or how mixed the data is once it is divided. So even that is, if it is less, that means it is more pure. And if it is more, it is the data needs to be further divided and it needs to be purified more. So that's what I understood.
Okay, great. Let's see somebody else. Sachin again. I don't think this is working right. Arpan Bandyopadhyay, you've been selected by the system for once.
This is we can use decision tree for classification regression for the problem. Good thing here is we can is rule based and we can see how data is going and how decision is coming part by part. We can see that node by node. And here we are having root and whatever root node and they have childs. So whatever childs we are having, if that child is having only one class, we cannot classify further. That is our leaf node. And if we can classify further, then we should classify and we should bring more child for that particular child. Now, how to do that? So first we need to calculate if we are having some 5, 6, maybe 4 features. So for 4 features, we need to calculate information gain. So that is formula I should tell.
No.
Okay, we should calculate the information gain. And to calculate the information gain, we need to calculate entropy or gain index for each. Now, after for all the features, for which feature is having more information gain, that should be our root node. And information gain is used to select the root node from where we split the data. And entropy or gain index we can use to check. We use to check the impurity. So it is the range is 0 to 1 minus 1 by C. C is
okay, good. Let's pick one more person. Thank you.
I can explain, sir.
No, that's okay. Tarun. Tarun is online or here? Online. Tarun, you want to explain anything you've understood so far?
I'm still reading the document, sir. Until I have read, people have already explained like
No
these two
problem.
methods, Gini and entropy.
Yeah. Okay. Kartikeyan. Anything you want to add on? Additional thing, not the same thing, additional things that we haven't covered. Nothing? Mohammed Idris? Okay. Deepika? Any other data points? All good? Sachin? You've already explained. Sunil Kumar. Do we have Sunil here online? He left actually. Then I will remove him. Karthik. I think we have already selected Karthik few times. Venkata. Sai or Venkata? Which one you go with? Huh? Harshit, okay. Harshit, yeah. Go ahead, Harshit. Okay, so why don't we then just go through the document? I think everybody's saying it's okay.
One is like as we split the data more and more, entropy or gain index should be lesser. So if it is reducing, we are doing distantly model is doing good. And for regression, and another thing is sleep node, if it is very less kind of classes, we can consider this as a leaf node. Another thing, if it is regression problem, then we will for leaf node, we'll average of it, whatever the leaf node we are having. The problem with this is if we are having very deep tree, there is a chance for overfitting because very low bias and high variance. And if it is not too deep, like 1-2 state we are using, like not stage, or it is not too deep, then maybe it will be underfitting problem we can see. We can see. So for that, we need to define the deepness of that tree, like how deep we need to where we should stop splitting. All those things we need to.
Yep. Okay, good. Thank you. That's right. Small data changes can lead to high amount of changes in the tree, right? So we will begin with the classifier, but it's also same thing for regression. So you can use a decision tree for building a regression model as well, right? So till now, what we've used for regression? Till now, we have used a linear regression, right? Linear reg for regression. And till now, what we have used for classification? We have used a logistic regression, right? Even though it says regression, we know it's a classification thing, right? Now we're looking at the decision tree, which can be a DTC or DTR. Decision tree classifier or decision tree regressor. Same algorithm will be doing that. But instead of just calling in the classifier, you'll be calling the decision tree regressor if you have a regression problem. It's as simple as that. So you can see the versatility of this method, right? Same decision tree can be used for classification and regression, but the instance that you'll be calling in will be different, right? This is non-parametric, so that means it does. So what do you mean by parametric, non-parametric? Like, in linear regression, we had this equation, right? Right. So like you will have some sort of equation that you're forming that is a linear or logistic, right? All of those things. It says there is no requirement for any of that relationship whatsoever, right? So I'm not assuming any linear, non-linear, this, that. It could be anything you give me and I will do a good job for you. More importantly, it is very interpretable, rule-based and hierarchical and very visual also. So you can visualize things, right? And it's almost like rules. You're creating the rules. So remember when we began the activity, we said if the petal length is less than 1.75, whatever that number was, that was nothing but a rule. If that is the criteria, then this. If that is the criteria, then this, right? So it's much easier compared to the previous algorithms for the interpretation, right? So it's if else sort of thing where you can write the rules. And it's a very business oriented interpretation, which is very, very easy for the non-tech audience to really understand what is happening as well, right? And it splits the nodes to create more homogeneous data, as you discussed earlier on. And it will recursively keep on splitting in all of that. And you will have basically the leaf nodes, the parent node. So this is a child node, and this child node becomes a parent node to the next child node, right? So like a grandparent, parent, great grandparent, all of that sort of thing. So that's what, and the end node is called the leaf node. There is nothing else coming out from that. Internal is like this. So if you're looking at the tree continues to grow. So even further it grows. So this becomes your internal node, right? This is part of your node only. This is Huh? It is a flow chart, but like, you're following a rule to come on this side, you're following a rule to come on that side. Like, yeah. So then, yeah, you can say it's like a flow chart only. So if that makes it easier for you to understand, yeah, definitely. Um, yeah, so it's very business oriented, very interpretable, very rule based, hierarchical. So it will go from one to second to third to fourth and so on and so forth, right? So it follows a certain hierarchy. Very, very important tool. Very, very important tool in the AI/ML repo that you're gonna build, that you are building a decision tree also, right? So how does it really work out? It finds the best split, and we'll be talking about the best later on. So basically, best meaning, whatever decreases the impurity the highest. And we're gonna measure the impurity by using two metrics, Gini or entropy, right? And for numerical value, it will decide the threshold. So for example, let's say the petal length was, I'm just making up a number. So the petal length was going from 1 till 5. It will figure out, do I apply a cut here? Do I apply a cut here? Do I apply a cut here? Right? And do I apply a cut here? Which one is going to give me the biggest gain in the impurity or biggest reduction in the impurity? And that will be chosen by the algorithm, right? And I mean, there are like, different ways. So for example, sometime it will just say, let's first do half, right? And then again do a half and then see, where exactly I'm finding the optimal. So I'm not going to go in the details of how the algorithm really works underlying, but let's understand some of the basic functionalities first, right? So let's carry on down. And then it will continue to split the data, repeat that process recursively and all of that. And then it will continue to go towards the end, right? And I think somewhere it also mentioned, yeah, over here. So it's non-parametric. That means it makes no assumptions about the data distribution. So you could be linear, it could be Gaussian, it could be exponential rising, it could be uniform distribution, it could be a step up, step down. Any sort of distribution is fine with a decision tree. That's like a big relief because so far we were all like, bounded that you must have a linear regression, linear relationship, you must have a logistic, like, the sigmoid and all of that. So it says, nope, I don't really care. Just give me the data, I will build something for you, right? So that's the beauty about this. It's a rule-based, if-else decision rules, hierarchical, and it's a greedy learning algorithm, right? So for example, over here, it decided that petal length is the best criteria. When it comes to this node, it will reevaluate all the features and say, including the petal length, petal width, sepal length, sepal width, what gives me the best split? And it will choose that. So it's a greedy algorithm. Every node, it will do a re-optimization and then give you the best split, right? And it's like a beauty. That's the beauty of that as well. And it will try to reduce the impurity, and impurity is being measured by the Gini index, right? So let's just talk about the Gini index first of all. So Gini is 1 minus all the different classes, probability of those classes squared, right? So for example, let's say if I have a class where 30% students are girls and 70% students are boys, what will be the Gini of that system? I'm not sharing. No, it is shared. Abhi will confirm that. Shared or no? Shared, yeah.
We can see, sir.
Okay, perfect. So what will be the Gini of this system? Anybody? Is this clear, everyone? So the Gini for this system, where we have 30% girls, 70% boys, will be nothing but 1 minus probability of finding a girl, which is 30%. Probability of finding a boy, which is 70%. So who can tell the math? What will be the impurity of this system? 0. Minus cannot be. If you square a decimal number, it becomes even smaller. 0.42 is a number I'm hearing from people. 1. 0.42. 0.4. Okay. 0.42 is correct then. So there is this amount of impurity. Now let's do the impurity for this class. No, not in the sense of don't take it literally, but I mean, let's say how many girls do we have in this class? 1, 2, 3, 4, 5. Correct, Abhi? Based on this class right now. Like, I mean, online we have some girls also. 5. So we have 5, let's say just the class which we have over here. So 5 girls and how many boys? Let's count very quickly. Just say 1, 2, 3, 4. Abhi. What are you? 21. So let's do 22. Acha, haan. You were quiet. You were deciding, huh? So what will be the entropy for this system then? So let's say 22 boys and 4 girls. What will be the entropy for this system? Sorry, 5 girls. My bad. 5 girls. What will be the entropy for this system? So 5 divided by 27 square minus 22 divided by 27 square, right? Is this clear? Now, is this entropy gonna be less than this or higher than this? Just like intuitive sense. I mean, you can do the calculation, but tell me whether it's gonna be higher than this number or lower than this number. How many people for lower? Raise your hand. Only one person. 2 people. How many says gonna be higher?
This number of higher number of words, so and more impure.
That's the point you guys, all of you missed, right? So Gini will be lower in this case. It is more pure system because boys are much more than the girls in this class compared to this. So here you had 30% girls, 70% boys. So this is more impure system versus this class where you have only 5 girls and 22 boys. So this is going to be much more pure system. So Gini will be lower. Let's do the math. Let's just confirm. I mean, don't believe my word. Just do the math. Huh?
More balance means more impure.
Exactly.
Imbalance means pure.
Exactly. So if it is one class only, let's say if it is all boys, what will be the Gini? Not Gino, Gini. It will be 0, right? Because there is no other class. Only one class is there. So there you have it. So just the intuitive. You don't need to memorize the formulas in your head. So just say higher the impurity, higher the Gini. Less the impurity, lower the Gini. So because I already gave you the hint, there's only 5 girls and 22 boys, right? So the impurity is less. So Gini is going to be much lower than this. Who has got the number? What is this number? 0.30, right? Okay. So you can see it is coming out to be lower, right? That's the main intuition behind Gini. So what is tree gonna do? It will say, you give me a Gini, I will figure out a mix to lower this Gini down. As I'm going down, I will continue to bam, 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 try to lower your Gini down so that I get more and more purity for you. So tree will try to lower the impurity, lower the Gini. Is this clear conceptually? Right? Without memorizing the formula and going into many details. So one of the algorithms that we use for building the tree is called the cart, right? There's another thing called shade and, some of the other decision trees. So, but the most popular is this. This is what we're going to do in the sklearn. This is, something that you can do in the other tools and softwares. I mean, shade also is possible over here, which is short for chi-square automatic interaction detection, which is a chi-square test of independence that you would have done in your statistics class, right? You've done the chi-square? You haven't done? You haven't done. So you'll be doing maybe in some future class, right? So, but I'll just leave it for there for now. A cousin of Gini is entropy. Now, same problem. Let's say I have 30% girls, 70% boys. What is going to be the entropy formula? Entropy is going to be nothing but P, which is 30 times 100 natural log of P This is a probability for the girl, like this girl portion, right? Minus this, correct? So this is the entropy. And I'll show you, I mean, I don't have the math over here. So Gini and entropy will have a max. So Gini entropy chart, binary data, binary only. So don't get confused. So Gini and entropy will behave something like this for a binary data, right? Which is Gini will max out at 50% for the highest amount of impurity. Gini will max out at 50% for the highest amount of impurity. It will come down as one class becomes higher. So for example, if it is all boys, Gini is 0. All girls, Gini is 0, right? When one class is overshadowing the other class completely. In between, when 50% boy, 50% girls, Gini is 0.5. Similarly, entropy will max out at 1, right? So you can do this math over here as well. So let's just do for Gini, for example, maxing of the Gini will be when both classes are equal number of times. So 1 minus 0.5 square minus 0.5 square, which is nothing but 0.25 times 2, which is nothing but 0.5, right? When both classes are present equal times, 50-50, highest amount of impurity, Gini will max out to 0.5. Clear? If you have 3 classes, then Gini will be something else and all of that. So I hope this gives you good conceptual underpinning, which is required for the next. Now comes the part of information gain that Arpan was talking about, right? So what the decision tree tries to do is either you can say it will try to reduce the Gini or entropy a lot from one node to another node, child node, from parent node to the child node, or it will try to maximize the information gain. What is the information gain? Is the entropy of the parent node, or you can say Gini of the parent node, that doesn't matter. So Gini of the parent node minus the weighted average of the Gini of the child nodes. So for example, if I have this node, I had a certain Gini, and then these two nodes, I have a certain Gini. I will take a weighted average Gini of this, and I will subtract from the parent node, and the resulting number is called the information gain. And the decision tree decides on the split where the information gain is going to be the highest. Where the drop in the, what is information gain? For a lack of no formula. So you can say information gain is nothing but the drop in impurity as measured by Gini and entropy. So how much drop I am able to gain? That's the information gain. So higher the drop in the impurity, higher the information gain. And that's what basically the decision tree tries to maximize, right? So let's do, and then these are some of the other algorithms that you can see, ID3 and CO45 and all of that. Yes, yeah. So, but there is a a flip side. So that's what we're going to come to. So, sorry, the tree is doing internally. You don't have to do it. The tree is maximizing the information gain or drop in the Gini. But just like, in the linear regression, you must understand what it is doing. So I'm just telling you how the tree decides to split forward. No, you can use either one of them. You can use that as a hyperparameter when we talk about the hyperparameter. You had a question, Ajit. Yes, yes. That's what it does internally.
Achieve the same thing. So how do we compare?
Other way meaning?
Like I can take any other attribute and do a classification.
No. So it will.
The petal speed is there.
Yeah.
Instead of petal width, I can take the petal length and still
And
continue.
it does that internally. So it's computationally intensive.
Yeah.
So it will do that internally to figure out the best split for you.
So the criteria is not the performance. Other
No, the criteria is the performance gain, information gain.
But there is a performance override to calculate that.
So what? So the algorithm is doing that computation internally only. There are tools where you can say, no, I don't want to split on this, right? I want to overrule and I want to split on this. Manually override. But I'm not gonna go there right now. So I'm saying let the tool decide. So the tool will say, okay, sepal length, sepal width, petal length, petal width, which will give me the highest drop in the Gini. So if I take you back over here, so what the tree is doing internally when you're building the tree is it did not come out with this magically, like, petal length is going to be the case, right? So it considered I need to evaluate petal length, petal width, sepal length, sepal width. It will say, what is the Gini over here? 0.6667. What is the Gini over here? Who can tell me the weighted average Gini for this system? So let's just do the information gain math so that you know what the tree is doing. What is going to be the information gain over here? So Gini over here is 0.67. Let's say we round it off. 0.67. What is going to be the Gini of this system? 0 times 50 plus 100 times 0.5 divided by 150. 0.75? Okay. No, it has to be lower. It has to be lower, right? Because the Gini is 0 here and then over here. So you can do the math. So whatever that maths turn out to be. Huh? 0.33, right? So 0.33. So the Gini has dropped by 0.67 to 0.33. This guy is nothing but information gain. So it will say, okay, if I do the split by petal length, I'm getting the information gain of whatever that number is. Let's say what, 0.34. I'm getting the information gain of 0.34. If I do by the petal width, I'm getting the information gain of 0.3. If I do by sepal length, I'm getting the information gain of 0.2. If I do by sepal width, I'm getting the information gain of 0.25. Hence, I will choose the petal length for breaking this tree down. That's the intuition. Yes, all the features will be checked again. This node will not be split forward because there's nothing to split. Gini is 0. The tree is happy. This will be again. Yeah, because you're not measuring the units, you're looking at the classes. No, you have to do the dummy coding of the variables. That will be the entire process remains the same for building any. That's why the 6 steps, 6 golden steps will remain the same. But I'm saying this. Yes, that's right. Yes, that's right. It's less sensitive to the outliers, to the scaling, to all of those things. So it's more robust from that point of view. So you can still go forward, but not necessarily needed, over here, right? So it's a good thing to do, but not necessarily needed because it's not doing any distance, any computation, anything of that nature. It's just saying what is going to make the better split. And that's what basically is considering, right? So that's how basically it grows. So you can see this decision tree is looking very deep, right? So let's talk about some of the metrics that you're going to see in the sklearn. What do we measure over here? And that's the hyperparameter we are trying to optimize. So how many levels of tree we have? How many how many levels do we have? This is the root node. First level, second level, third level, fourth level, fifth level. So this is called depth. How deep your tree is going to be. Higher the depth, higher the complexity, higher the overfitting of the tree. So this is one big parameter that you have to try to prune the tree. Just like, you have put a plant in your house, the plant becomes a tree. Now trees like overshadowing your entire house, right? You're going to prune it. Same thing happens with the decision tree in our machine learning world, that you have to prune it. One of the way of pruning it that we can say, please do not grow beyond 3 levels of depth. So stop over here, right? The moment you say, the tree is gonna stop. Or you can specify a criteria that do not split forward until you have a bare minimum number of members in that node, right? So for example, do not split forward unless you have 25 members. Will be one criteria that you can specify, that you should only split when you have 25 members. If you do not have 25 members, do not split. So which node will stop? Where do you think the tree is gonna stop? Will this stop? This has already stopped. So you tell me whatever you want to do. I'm just gonna ignore because there's nothing I can do. I'm done, right? Will this stop? No, because you still have 100 members. So this will be split forward. Will this stop? Nope, split forward. Will this be stopping? Nope, further split. Similarly, not stopping here, but this will not be split forward because I'm violating this criteria that, I mean, you should not split until you have 25 members. So it will be not split forward. Will this go forward? Nope, it will also not go forward. This will go forward, but because there is no impurity, this will also stop. So you can see there are many mechanisms of, tree to stop growing wildly. Otherwise it becomes a very, very wild tree. And similarly, there is one more criteria, which is how many members do you want to have in each node, right? So for example, I can say minimum, I want 50 members in each node, including a leaf node. Including a leaf node, I want a 50 members. So after you've done your split, you should still be remaining with 50 members. So is this following the criteria? Yes, it is, right? Is this following the criteria? Yes, but it will not be split forward. Why? Because this doesn't have a 50 and this doesn't have a 50. So it will stop right over here. Are you guys understanding? Because I said, okay, you can split only after the split. You are able to ensure that you have a minimum of 50 members in each of your leaf node. It says, okay, let me try, but it says, okay, I'm violating your criteria. I'm 48 and 6, so I should not do it. So I'm going to stop here. It will be pruned over here. How about this guy? Will this go forward? Nope. This will also not go forward. So it will stop right over here, right? So this will be the end tree that you're looking at. So how many ways we can do it? Either Gini or entropy becomes 0. One criteria. Max depth. Third is how many minimum sample you must have in the leaf node. And then how many minimum you need to have for splitting forward. These are the 4 main parameters that we control for building a tree. Is this clear? So now comes the fun part where you're going to build your own decision tree on Titanic data, but I'm going to give you a high level. I'm not going to share this notebook with you right now because I want you guys to be building that. So I'm going to just walk you through so you understand what we're going to, everything. We're not dividing. The tree automatically knows that I cannot split forward if the Gini becomes 0, right? Everything will remain the same as you've done in the logistic regression. So leverage the same data. Nothing changes at all. No changes at all. Everything remains the same. What is going to change will be the first thing over here. I'll give you guys a minute to take a look at this. I'm specifying the criteria as Gini. Max depth is equal to 3. Remember, we said how many levels you can go deep. So I'm saying only 3 levels deep you can go. Min sample leaf is 50. That means each end node must have 50 members. Min sample split is 75. That you can only split when you have 75 members in it, right? Just for my way of pruning the tree. This is called the pre-pruning, not the post-pruning. Pre-pruning. I'm pre-pruning the tree. Then I'm going to fit my decision tree. Then I will basically same thing as this, and then we're going to do the prediction, and then it will come back with the whole evaluation matrix. Some of this may make sense, other may not, right? So depending on what we're looking at. And then the main part is we're going to visualize the tree, just like what we have done. So this is the assignment for you. Without knowing the notebook, you have to do because you already have the source code that you can leverage. Not able to zoom out for some reason. Yeah.
Because both are same.
Optimize, hyperparameter optimization. Hyperparameter optimization. So I'll just explain you what this tree is and let's see if somebody can help me. So in this case, I have How many observations in my root node? Anyone?
7,
7, 1, 12. And how many of those are the survivor? Sorry, 0. It says the majority class. Majority class is 0. So 4, 34 zeros and 278 ones. So mostly people did not survive, right? Is this clear so far? So 434 zeros, 278 ones. So, and then adding up to this number. Gini is coming out to be this. I don't need to show you the math, but you can do the math. 1 minus 278 divided by 712 square minus 434 712 square will be this number, Gini, impurity, right? And it has chosen the criteria. Yeah. Zoom, acha. But you will not be able to see the full tree. That's the thing. I'll come back to it in a minute. So, and then it has applied one criteria. So let me zoom in on this one so that you see one branch of the tree. Let's just focus on this so far, right? It has already applied the criteria. It says if the gender is less than or equal to 0.5, what does it mean? If you remember the dummy coding in Titanic. 0 and 1. Yeah. So what does it mean if gender is equal to less than or equal to 0.5?
female.
Right. So we have female and male. So female was dummy coded as 0, male was dummy coded as 1. So it says if your gender is less than or equal to 0.5, that means all females, please come on this side. All males come to this side. Exactly. On each node. So it is computationally intensive. So it will say if all the features at each node I must evaluate to decide what happens.
After level 1, that factor is not.
It may again come back, but in this case it's all female. So now gender is irrelevant. But there are cases where the same variable may again come back.
Length and width.
Again come back. Yeah, it can again come back. So it says, it says all females on this side, all males on this side. What do you make out from this data? They're all females only. They're all females only. So now the class is 1, majority class is 1. So that means out of 266 females, 198 survived. That's a huge survival rate, right? 198 out of 266. Out of the poor males, 446, only 80 survived. Right? This is real life data in Titanic. Huh? Yeah, they were given the boats first. So they were given the boats first that you should go. Ladies first, yeah, boats first, right? So you can see how powerful the decision tree is. I mean, we were building logistic regression, we got an equation, then we said, what is the coefficients and so on and so forth. It gave you a rule right here that if you're female, your chances of survival is nothing but 198 times 266, which is upwards of 80%, I think. I mean, if I do a rough math, right? You're 80% likely to survive. If you're a male, God helps you, right? 20% survival probability for you, right? So, and it goes on and on. I mean, so it's not done yet. So that's the beauty of a decision tree. It says, okay, fine. Even if you're female, let's see what else will be deciding your future. It says, okay, if your passenger class, which class you are traveling on? If you are traveling first or second class, please come over here. If you're traveling third class, again 50-50 odds of survival. So even within the female, rich females were given the preference to get onto the boat first, right? So all the females which were traveling in the first class or second class, out of 143 such females, 135 survived. 8 may have not survived because of their own stupidity, right? Or I mean, they were just unlucky or whatever, right? So they were given the first preference. If you're a rich female, please go, right? But then there were poor females who were traveling in the third class or doing some work, you know, in the bottom of the ship or whatever, right? So they had a 50-50 odds of survival. So this is the beauty of a tree. Where, sorry? It just says which is a majority class. Here. This one. Where below? Here, this. So majority is 43. So here zeros are more. Zeros are more. So whichever is more is given the like number here. So 198 survivals. 135 survivals. 63 survivals. Right? Which value? This. What value? Yeah, so this is like the distribution. So in this node, you are left with 123 females. They're all females. So the moment you step into this side, all the oranges are male, all the blues are females. So this says if I'm in this node, I have 123 females in this node. Out of 133 females, 63 females are survivals, 60 females are non-survivals. You understand? If I'm in this node, which is what is this node? It says if you're female and traveling first and second class. So there were 143 females who were traveling first and second class. Out of those females, 135 survived. 8 did not survive. Is that clear? Because that's the objective. That's what it's trying to classify. Right? So every single node that you're looking at, it will keep on giving you that number. It will say survival class 1, class 2, class 0, like this. So if you're multi-class, it's going to give you multi-class as well. So let's see who is very good in interpreting this before you start the actual hands-on work. Those are the samples. Those are the samples. I'll come back to it. Okay. What is the, sometimes it works, sometimes it doesn't. Control minus, or what does it take? I have to be out of this, I think. Yeah, in this one. So let's say who has the poorest survival rate from this tree? Who will have absolutely the worst survival rate?
Many who have got no ticket which is low.
No, from this tree only. So first of all, I'm already giving you a hint that the darkest the color, the purest the node. The darkest the color, the purest the node. So look at the darkest and purest node first. If I'm correct visually, I think it's this guy right here.
Here,
No, I'm saying the worst survival rate. Worst survival rate. It is dark, the darkest. Right. So, and what it is, it says you have 259 people in this node, 259 people, and they're all male, by the way. So let's look at the rule. So 259 males, out of those, 22 survived. Right. So that's like, 10% survival rates, or even, yeah, slightly less than 10, in fact, 9% maybe survival rate. Only 9% such males survived, right? What are those males? So they are paying less fare. So they are paying less than 22, 26 pounds, and they are young people. They are young people. They are less than 20 years old. So these,
age is greater than 28.
sorry, my bad. So it's false. Yeah. So age is more than 20, not children. Age is this. So this is the branch we are coming on. This branch is going to take us to this node, right? So that is, this branch is male. This branch is fare is more than, sorry, fare is less than, yeah, fare is more than 26 actually, in fact, in this, yeah. And then the age is more than 20, whatever that number turns out to be. So these are the people. And who has the best survival rate? For example, this, right? which is fair is more than 29 pound and all of that. And there are 81 females and only 2 females did not make it, right? That's the beautiful thing about this decision tree. So why don't we start? And everybody should confirm you have something like this. And then we'll take it forward. The next activity that we'll be talking about will be after this, after you built your tree and we have taken a break, we'll be talking about something called as a cross validation, right? Cross validation and hyperparameter optimization. Hyperparameter optimization. I think that will be the end of the day in my view. I think those are going to be meaty topics, and threshold optimization. Those 3 topics. So I'll wait for all of you to confirm whether you are done with this. You can in the tree you can do some methods. I'm sure it will give you the rules. There is something I don't recall right now, but there are like rules that you can get. I'll wait for all of you to confirm whether you're done.